All right, let's talk about our intermolecular forces. So I'm going to be up front here. This should all be a review. All right, this is all stuff we go over in our prep class. In fact, most of the slides I'm using here are a repeat from the ones that I use when I teach the prep class. So as you're going through this, the hope is that it is a jog to your memory and not brand new information that you have never seen before. All right. Now, the first three forces I have listed here are dispersion forces, are dipole-dipole, are hydrogen bonding. These three forces are all ones that can exist in a homogeneous sample of a substance. They can also exist when I have two different substances mixed together. The ion-dipole that I have at the bottom there, that one, however, requires two different substances to be mixed together. All right, so let's talk about our dispersion forces. Now, this is kind of interesting because this is a common issue in science where we had some sort of vernacular that we used for something, and then something came along and either had a better name for it or just ended up changing the name. And, well, the old name stuck because people get, tunnel vision and pigeonholed into something. So I have London/dispersion on here because London forces are the old classic name for this, but dispersion is the better name because dispersion really describes what we're actually seeing here. This type of force is in everything, okay? In all substances. Okay, so these dispersion forces are in everything. And so what we're looking at is we're looking at a force of attraction that happens when we have some sort of instantaneous disruption of those electrons that are in an atom or in a molecule. So what's happening is everything has electrons, right? And we know that electrons are not static in place. They move around. And so electrons are negative. So let's say something comes along that's positive and attracts all of those electrons off to the side. Well, now what happens is we have a situation where I've got a concentration of negative charge over here from all the electrons and a dearth of negative charge over here. So more positive charge from the nucleus because all the space is empty. And so what we see is a domino effect, a cascade where now that something else comes near it, now that happens to that one and that one happens to that one. And so it's this domino effect. And so our nonpolar substances, this is the only force that we're seeing in a pure sample of a nonpolar substance, because in something nonpolar, there's no permanent positive and, permanent negative end to it. It's just this, polarizability that's happening here. Okay, and so if I've got something like liquid nitrogen, that's nonpolar. Well, liquid nitrogen happens because we get these instantaneous polarizations. Now, polarizability, what is that? All right, well, when we talk about polarizability, the more polarizable something is, the easier it is to disrupt that electron cloud. So when I look at the ease with that electron cloud of a molecule or an atom can be distorted. And so when that gets distorted, we induce that dipole moment. If I have more electrons, I'm going to increase that polarizability because think about it. Where are we going to get a stronger concentration of negative charge? Something that has 1 electron or something that has 25 electrons? Well, obviously 25 electrons. And so we get more polarizability when we increase the number of electrons. And so here's a visual here. So I've got, a substance with 2 electrons. In the first two frames, everything's moving along, okay? But now in frame 3, both electrons end up on the same side. Now this could happen because something comes along and induces that to occur, or it could just happen naturally because again, do electrons stay in one place? No, they do not. They're constantly bumping around. And so we get both the electrons on one side. Well, again, now I've got this instantaneous partial negative. It may only last for a moment, but if there's other particles next to it, now, as the bottom picture shows, now we induce that across the sample. All right? And so when we think about the dispersion forces, we can think about it being an induced dipole. And so these are the interactions that we have between nonpolar substances. Now again, these are still in everything. Even if something is polar or at hydrogen bonds, those forces are usually going to be stronger than the dispersion forces. However, dispersion forces still exist because in a polar molecule, do I still have electrons that move around? Absolutely, I do. Okay, and so A, just the pure sample, nothing's happened, and in picture B here, now we've induced that dipole and we've caused these dispersion forces to happen. When I look at my dispersion forces, all right, the strength of these forces is going to increase with the number of electrons, right? So the strength of our forces increases with the number of electrons. Typically, that correlates to molar mass because if I add more protons, I've also added more electrons for a neutral ground state species. Now, one interesting thing is the boiling point gets higher going down our groups for our halogens and noble gases, because if the strength of dispersion force increases, well, that means it's going to take more energy to go from the liquid phase to the gaseous phase. And so stronger intermolecular force, higher boiling point. And we see this, like if you look at fluorine versus chlorine versus bromine versus iodine, this trend is really easily seen in our halogens because fluorine and chlorine at room temperature, those are gases. Bromine is a liquid and iodine's a solid. And so we see this trend very clearly with our halogens. Okay, if I look at some straight chain molecules, so straight chain, all right, the larger they get, the more the boiling point goes up. Now, this is actually happening because of two things, though, okay? One, pentane has a smaller molar mass than nonane, right? 5 carbons versus 9 carbons. But if you look at the size, is there a difference in the size there? Absolutely. Because remember, these forces are holding things together. And so if I have a small area of these things held together, there's not very many points of attraction. But if I have something bigger, I have more points of attraction. So not only does nonane have a larger molar mass, but nonane is also bigger physically. And so there's more points at where there can be attraction that drives the boiling point up. We can compare this even in something that has the same formula. So two isomers, N-pentane and neopentane. These are isomers of each other. They have the exact same number of carbons and hydrogens. But N-pentane has a boiling point of 36.1 degrees Celsius, where neopentane is only 9.5. Why is this? It's the size of the actual molecule itself. N-pentane is a straight chain hydrocarbon, so it's longer, whereas neopentane is a ball. So if I look at my hands, all right, everybody agrees that, my hands are not changing. If I go from here to here, right, it's still my hand. But if I hold my hands like this versus like this, where are there more points for my hands to rub against each other and attract each other? When they're flat like this. When they're balled up, it's smaller, and so there's less places for those attractions to occur. Okay, and so you can see there, large area for attraction, small area for interaction. All right, now when we look at our dipole-dipole forces, we've got a permanent positive end and a permanent negative end. And what do we know about opposites? They attract. And so there's a permanent ability here for there to be an attraction between a positive and a negative end. So our dipole-dipole forces, we sometimes call polar-polar forces. Our solids are going to be a lot more regularly arranged, whereas our liquids are going to be a little bit more on the chaotic side. When I look at boiling points and melting points, okay, if I look at formaldehyde and ethane, they have very similar molar masses, but the difference between formaldehyde and ethane is that formaldehyde is polar and ethane is nonpolar. Okay, so this is polar, nonpolar. All right, and so when I look, the boiling point for formaldehyde is negative 19.5, whereas ethane is negative 88. So they're both very low boiling points. However, ethane's is much lower than formaldehyde because the forces that hold ethane together are not as strong. Now notice that I'm comparing two things with similar molar masses. When we start to look at molecules with large size differences, then the story changes. Because if I have this giant hydrocarbon with tons of points of attraction, it's going to have very strong dispersion forces. Whereas by the teeny tiny, polar molecule, it's going to be a little bit different. Okay, so we're comparing things here of similar sizes. Okay, and when I look here, if I look at propane up through acetonitrile, and I look at the size of the dipole moment, propane has almost no dipole moment to it, whereas acetonitrile has a fairly strong dipole moment. And which one has the higher boiling point? The one with the stronger dipole. And again, if you notice, the molar masses are printed on here. So they all have similar molar masses. So in molecules of similar size, that size of the dipole moment is going to be the determining factor on that boiling point. Okay, now let's talk about my personal favorite, hydrogen bonds. Okay, so these are a very special type of intermolecular force. You have to have a nitrogen, not a nitrogen, I'm looking at the nitrogen while I'm saying this. You have to have a hydrogen that is bonded to a small, highly polar molecule or atom, such as nitrogen, oxygen, or fluorine. If the hydrogen is not on one of those four, you do not get a hydrogen bond. Okay, so what's happening here? It is a dipole-dipole force. All of these are going to be polar molecules. However, what we're looking at is we've got these hydrogen atoms bonded to these small, highly electronegative atoms with lone pairs. Okay, and that's going to be your oxygen, your nitrogen, or your fluorine. Only those three. So these guys are super electronegative. And what do we know about electronegativity? It's a measure of what? Electron greed. And so why do atoms bond? Well, they bond to fill those valence shells, right? Hydrogen, when it bonds, it only needs a duet, all right? Nitrogen, oxygen, fluorine, they all want their octet. So who's holding the electron stronger? The less electronegative element or the more electronegative element? The more electronegative element. So we know in a polar bond that the electrons are held unequally, all right? A pure covalent bond, total equal, there's no difference in electronegativity. But a polar covalent bond, there is a difference in electronegativity. And what we see is the more electronegative element attracts the electrons stronger. And so what happens is the electrons spend more of their time around the more electronegative element. And the less electronegative element is left going, wait a second here, I bonded with you to fill my valence shell. And those electrons are not spending a whole lot of time with me. And so it has this dearth of electron density. And it needs to fill that electron density somehow. And that's where a hydrogen bond comes into play. Now, it's called a hydrogen bond, okay, not actually a bond. Okay, it's not actually a full bond. It's still just a tether, all right? It's still just a molecular tether. However, it's a fairly strong molecular tether. And so if you have something that's highly electronegative with lone pairs, it is flush with electron density. And it's very attractive to those poor atoms that are just not very electronegative and don't attract electrons as strongly. And so they want to hang out together. And so those tethers are formed. Okay? Some interesting facts about hydrogen bonds. They are strong, but they're still typically less than 10% the strength of a covalent bond. And just some cool stuff. Adhesives, a lot of those act with hydrogen bonds. Shapes of proteins, which we'll look at in a little bit, are very hydrogen bond dependent. Cellulose is super strong because it has a lot of hydroxyl groups, and so we get hydrogen bonds there. Okay? Now, when I look at these, okay, now water is pretty cool because we can get these 4 simultaneous hydrogen bonds to it. Now, I personally, as a chemist who studied hydrogen bonds, don't really like some of these pictures. When we draw a Lewis structure, we depict lone pairs with dots. So I don't like these pictures that show hydrogen bonds with dots. Okay, there's a better way to show a hydrogen bond. And if you're in one of my classes, this is what I'm going to expect out of you. Okay, so students, in my class, this is how I expect you to show a hydrogen bond. With a dashed line, not with dots. They're not electrons, and it's not a full bond. And that's where the dashed line comes in, is we draw bonds with those straight lines, right? And so the dash shows that it's a fairly strong tether, but it's not quite as strong as an actual bond. Okay? And so now what's interesting over here, I have ethanol. Okay? And so I've got a carbon to a carbon. And so I show in this image, a hydrogen bond between the oxygen and the hydrogen that's on oxygen. And so this hydrogen can participate in hydrogen bonding. These guys, because they're attached to the carbon, they cannot participate in hydrogen bonding. Okay? Now what's interesting is that oxygen can always participate in hydrogen bonding. Let's say I mix something like ether and ethanol. Ether, here's the simplest ether, dimethyl ether. One of these days, I will figure out how not to accidentally hit the color selection palette at the bottom. So let's say I mix that dimethyl ether with my ethanol. That oxygen can always accept a hydrogen bond, okay? Because it's still an oxygen and it still has lone pairs. So the oxygen can always accept, the nitrogen can always accept, the fluorine can always accept. They can always accept a hydrogen bond. But the hydrogen that participates in the hydrogen bond has to be bonded to the oxygen, the nitrogen, or the fluorine. Okay? So let's take a look here. I have some molecules. We're going to figure out which ones exhibit hydrogen bonding, and then we're going to show the hydrogen bonds. So our first one here, the C2H6, is that one going to hydrogen bond? Yes, no. He said no, you were correct, because the hydrogens are only on carbons. All right, now methanol, are we going to hydrogen bond there? He said yes, you're good. Now, are all 4 of those hydrogens going to participate in hydrogen bonding? No. Okay, these 3 cannot hydrogen bond, whereas this one can. All right, and that last crazy molecule I have, can that one hydrogen bond? Yeah, because these 2 hydrogens are attached to the nitrogen. These 3 hydrogens, though, cannot. Okay, so we have 2 molecules that we can show some hydrogen bonding between. All right, so methanol is very simple. So there's 2 molecules hydrogen bonded together. Now this other one's kind of interesting because remember what I said about the fact that the oxygen can always accept a hydrogen bond? I'm going to show you something with this one. Okay, and then we have, all right, so that's what that molecule looks like. Now, watch this. Because of the way that molecule's geometry is, you can actually get 2 simultaneous hydrogen bonds with it, which is really cool. And so yeah, so even though the oxygen doesn't have a hydrogen on it, it can still accept a hydrogen bond, as long as that hydrogen has been bonded to an oxygen, a nitrogen, or a fluorine. That other hydrogen on this nitrogen here, I could draw this. We could get a hydrogen bond like that too. That's totally possible. Okay, so a couple of different ways we can hydrogen bond on there. Now, some really cool stuff with those hydrogen bonds. All right, if I look at ethanol and dimethyl ether, these have the exact same formula, exact same molar mass, but when I look at those boiling points, what do you see? Well, ethanol has a much higher boiling point than dimethyl ether. Dimethyl ether vaporizes before we even get to room temperature, whereas ethanol, we have to heat it up a little bit. And that is the amazing strength of that hydrogen bond. So we can hydrogen bond in this one, and this one only has the dipole-dipole, well, and the dispersion forces. You know, our ethanol is going to have high dipole-dipole forces. The ethanol is going to have dispersion forces, but the strongest force there is that hydrogen bond. Okay? Now, when we look at our group 4A, 5A, 6A, 7A hydrogen-containing compounds, we can extrapolate. If I look at our group 6A, which oxygen is part of group 6A, okay? So that's going to be this red line here. If I look at tellurium, selenium, sulfur, you know, my boiling points are going down. But then what happens when I get to oxygen that's next to sulfur? It shoots straight up. We also see a difference in the boiling point with hydrogen fluoride and ammonia that does not follow the trend we would have expected from the other elements in groups 5A and 7A. Whereas group 4A, everything follows that trend. It steadily goes down with that boiling point as we go from, you know, lesser or lower down to higher up elements. So i.e. we, you know, the tin has a higher molar mass than the carbon does, which is why it has a higher boiling point than the methane does. But what's happening with water? What's happening with hydrogen fluoride? What's happening with ammonia? It's the hydrogen bonds. The hydrogen bonds are such strong tethers that going from that liquid phase to the vapor phase takes a lot more energy. Now, if you look at the slope of how it pops up, water pops up a lot more than hydrogen fluoride and ammonia do. If we look at water, you know, what's cool about water? Well, I have 2 and 2. I have 2 hydrogens and 2 lone pairs. So I can get 4 simultaneous hydrogen bonds to water. But if I look at ammonia, and I look at hydrogen fluoride, I have an unequal mix of hydrogens and lone pairs. So I don't get 4 simultaneous hydrogen bonds to every single molecule. So whereas those hydrogen bonds are strong, we're going to get stronger hydrogen bonding in water because 4 hydrogen bonds is a lot stronger than 1 or 2 or 3. Okay? All right, so if you don't like bar graphs, line graphs here, I have the exact same thing for you in a bar graph where you can see they point up. All right, so this is just an alternate viewing if this is easier for your brain to take in. Now, the cool thing about hydrogen bonds is so much around us is held together by hydrogen bonds. When I look at DNA, if you've ever wondered why we have the base pairing that we do, the adenine to thymine, the guanine to cytosine, it's because of hydrogen bonds. Okay, if I tried to pair up, say, the thymine with the guanine, okay, that oxygen at the top and that hydrogen on the top from the nitrogen, that would hydrogen bond. The middle, we couldn't get hydrogen bonding because the geometry would have those 2 hydrogens pointing straight at each other. That's not going to work. And then the bottom, we'd have 2 oxygens pointing at each other. Also not going to work. And so these base pair, because of the way they align with their geometry, to get 2 or 3 simultaneous hydrogen bonds. So that is why base pairing happens the way it does in DNA, hydrogen bonds. Okay, when we look at proteins, there's a lot of things that happen with proteins that deal with their folding. So a protein works when it has the quaternary structure that's correct. All right, so you get the primary structure, which is just all the amino acids that are linked together. The secondary structure is when it starts to come around each other. Then we get these sheets as they start to link up with each other. And then as the protein folds, that's where we get the correct structure and the activity that the protein shows. And so there's a lot of different things that are happening. Okay, it's not just hydrogen bonds, but one of the primary things that causes a protein to fold correctly is hydrogen bonds. And so misfolded proteins occur when you have a wrong sequencing of amino acids. And so a wrong sequencing of amino acids means that things aren't going to line up correctly. We're not going to have the hydrogen bonds where we're supposed to have them. We're not going to have the disulfide bonds where we're supposed to have them. All sorts of those things. And so This is why it's crucial that the amino acids sequence correctly, because otherwise it doesn't fold correctly. Okay, and then the last concept we're going to look at here is just this ion-dipole. We see this, like, let's say I dissolve an ionic substance in water. So I have, you know, an anion or a cation. Those are going to be attracted by the partial positive or the partial negative ends of something that has a permanent dipole to it. All right, so these are the four that we looked at. And so our dispersion forces are the weakest. Next is our dipole-dipole, then hydrogen bonding, and then our ion-dipole. Those are much stronger. All right, and so these are our forces. Okay, so now we're going to take a look at some substances here. We're going to figure out the dominant intermolecular forces in each substance, and then we're going to figure out if we can tell the one that has the higher boiling point. Remember, stronger intermolecular forces, higher boiling point. All right, so magnesium chloride or phosphorus trichloride. The way I named this should give you a hint. This is an ionic compound. So the dominant force is going to be an ionic bond. Okay, phosphorus trichloride. Okay, so does it have dispersion forces? Yes, it does. Is it polar? Yes. So does it have dipole-dipole? Yes. Any hydrogen bonding? No. So, okay, dipole-dipole is going to be your strongest force there. So which one's going to have the higher boiling point? The one with the ionic bond, the intramolecular force, or the one with the dipole-dipole force? Well, obviously this one. Okay. All right. So for the last few, I'm just going to tell you the final answer. I want you to figure out what the dominant force is and why the answer is what it is. All right, so this is going to be that one. Okay. All right, this one's going to be kind of interesting. This one's going to have two competing factors here because they're both have a hydroxyl. All right, and when we think about it, we're looking at, you know, a carbon chain with that hydroxyl on it. So they both will hydrogen bond, but there's going to be another competing force there. See if you can figure it out. And then hexane and 2,2-dimethylbutane, if you look at all the carbons and hydrogens, they're isomers of each other. They have the same formula. So I'll tell you that the hexane has the higher boiling point. Okay, so see if you can puzzle these out. These are the exact same examples that I give when I teach the prep chem class. So again, this is supposed to be a review here. So that's why I want to challenge you to see if you can figure out what the dominant force is and why the higher boiling point compound is the one that I circled, because this should be a review. If you're in one of my classes, if you're looking at these going, oh my goodness, I have absolutely no idea what you're talking about, this is definitely something to review and a good thing to come ask me questions about during office hours. All right, so those are intermolecular forces. Now, next up, we will take a look at the physical properties, well, a lot of them. We're going to save vapor pressure for its own consideration, but we're going to look at several of the other physical properties substances have and consider how these intermolecular forces influence those physical properties.